Hello, statistics students. My name is Emigh, and this video is our discussion on section 4.2. Title is Addition Rule and the Multiplication Rule. A standard deck of cards has 52 cards in it, and it is used a lot in learning the addition and multiplication rules and in statistics. So I want you to know how the deck of cards is composed. What I mean by that is I want you to know that half the deck is red, so there are 26 red cards. The other half is black, so there are 26 black cards. There are 4 suits. First one is hearts. So 52 divided by 4 is 13. So there are 13 hearts, 13 diamonds, 13 clubs, and 13 spades. There are 12 face cards, and those are these ones right here, the jacks, the kings, and the queens. There are 4 jacks, and that's the same for, there are 4 aces, 4 twos, 4 threes, 4 fours, 4 fives, 4 6, 4 sevens, 4 eights, 4 nines, 4 tens, 4 jacks, 4 queens, and 4 kings. Okay, there are 2 reds of every card. So what I mean by that is, let's go with the 4 jacks example. 2 of those are red. So jack of hearts and jack of diamonds. There are 2 blacks of every card. So let's go with the jacks example again. There is the jack of spades and jack of clubs. Okay, so a deck of cards is a nice tool for learning how to apply these statistical rules. So do make sure you know how the deck is composed, and you can refer back to this slide if you need to. All right, compound events. The last video section was just on one simple event, but we're going to talk about combining 2 or more simple events. So what you see here in the parentheses is A or B. So the capital P, remember, is read the probability of, and then it would be event A or event B occurs. Or both could occur. So with the statement with the word or, it means A or B. But if they both occur, that counts as or as well. A or B or both. All right, here is a Venn diagram in which the simple event A and the simple event B are not connected in any way. You see those circles are totally separate. And if that is the case, if there's no overlap in the probability of event A and the probability of event B, then the addition rule is applied. When you have the word A or B, you take your probability of simple event A plus sign and your probability of simple event B. Let's look at that with an example. What is the probability of drawing one card and it being a 2 or a queen? All right, these 2 events can be represented in the Venn diagram above. There are 4 twos. Let me change colors so you can see this. So you have the 2 of hearts, you have the 2 of diamonds, you have the 2 of spades. Ooh, not easy to draw with my finger here. And you have the 2 of clubs. Okay, and all of the queens, there are 4 queens. We have the queen of hearts, we have the queen of diamonds, the queen of spades, and the queen of clubs. This is awful. Okay, so you can see there's no overlap. There's no single card in the deck that would fall in the red circle and in the yellow circle. All the 2s are separate from all the queens. Okay, so that being the case, you will just take the probability of drawing a 2, you'll do a plus sign, and then the probability of drawing a queen. Okay, So I want you to set up your fractions, if you will. I don't want to show it yet. There it is. Okay, so setting this up as a blank template, I'll do it over here. That would look like your first fraction is the probability of drawing a 2, then a plus sign. Then your second fraction is the probability of drawing a queen. I like to set a blank template up like this. It just reminds me or gives me direction in a way that tells me I need to fill in 1, 2, 3, 4 blanks. So don't focus on all 4 at the same time. That can be too overwhelming. I just want you to focus on the probability of drawing a 2 for the first fraction. Okay, so the denominator is the total number of cards in the deck, so 52. And then the numerator is how the number of successes. And remember, whatever's inside the parentheses is what's considered a success. So how many 2s are there? And the answer is 4. Okay, now get that out of your mind and focus on the probability of drawing a queen, completely separate from drawing the 2. There are still 52 cards in the deck, and 4 of them are queens. All right, let me erase all this clutter. I think I just hit, there we go. And there are those 2 fractions set up for you, or a little nicer rather. Now adding fractions, you need a common denominator, which we already have. Adding the numerators, that means that there are 8 possibilities of success out of these 52 cards. And that makes sense because there are 8 2s or queens in the deck of cards. So 8 out of the 52 would be considered a success. That fraction does reduce to 2 over 13. So you want to give that in its simplest form. All right, let's look at this Venn diagram where there is an overlap in A and B. If there is an overlap, it's no problem. You start the exact same way. You have your fraction for the probability of A, plus sign, your fraction for the probability of B. Now this is where the difference comes in. You then have to subtract out the overlap. The reason why is it was double counted. So this overlap right here, it was counted in your first fraction, in your probability of A, but then it was counted again in your second fraction, the probability of B. So since you counted it twice, you just have to subtract it out 1 time because it needs to be counted once. All right, let me erase all that and let's try that to apply that rule through an example. What is the probability of drawing 1 card and it being a 2 or it being a red? Okay, so we know that there are 4 2s in the deck. We have the 2 of, I'm going to put the spade over here because that would not overlap, and the 2 of clubs, but the 2 of hearts is red, so it would actually be in the overlap, and the 2 of diamonds is also red, so it would be in the overlap. And the other red cards, that would be the ace of hearts, the ace of diamonds, the 3 of hearts, the 3 of diamonds. I'm not going to have enough room to draw all these in here, but there are 26 red cards. So 26 cards are in this yellow one. And let's see, and there are 4 cards in our red one. And 2 of the cards are overlapped. Okay, so we're going to set it up as the probability of drawing a 2, plus sign, the probability of drawing a red, minus sign, the probability of the overlap. So setting it up as a blank template would look like this. Don't have much room here. Fraction bar, plus sign, fraction bar, minus sign, fraction bar. So you have 1, 2, 3, 4, 5, 6 blanks to fill in. The probability of drawing a 2 we know is 4 out of 52. The probability of drawing a red is 26 out of 52. and then our overlap, 2 cards were double counted. So subtract those out. Here it is written up nicer for you. And we have a common denominator, so we do 4 plus 26 minus 2, which gives us 28. And that does reduce to 7 over 13. So the probability of drawing a 2 or a red card is 7 out of 13. All right, and that is the addition rule for disjoint events and not disjoint events. Let me erase all that clutter real quick. Oops, wrong button. There we go. All right, I want you to please pause this video now and try this example. Welcome back. Let's see how you did. These are disjoint events, drawing an ace, a king, or a queen. Those are all separate. It would, the notation would look like this: capital P, open parentheses, ace or king or queen. Since there's no overlap, we would just take the probability of an ace, plus sign, probability of king, plus sign, probability of queen. Probability of drawing an ace is 4 out of 52, plus probability of drawing a king is 4 out of 52, plus the probability of drawing a queen is 4 out of 52. And that gives us, let's see, 4, 8, 9, 10, that's 12 over 52. So if you got to 12 over 52, nice job. One last step would just be reducing that fraction to 3 over 13. Okay, that was all on the addition rule, which takes place when the word is or, this event or that event. But the multiplication rule is applied when we have the word and. This event occurs and that event occurs. If that's the case, we're going to apply the multiplication rule. If our events are independent, so kind of like the Venn diagram where there was no overlap, that being that the occurrence of one event occurring does not affect the probability of the other event occurring, then what we're going to do is take the probability of event A occurring, multiplication, the probability of event B occurring. If your events do have an overlap, or the probability of one event occurring is affected by the other one occurring, then we have to change our formula a little bit. It starts out the same, probability of event A, multiply, but then this is where the difference takes place. This right here is red. The probability that event, I'm reading it right from here, okay? The probability that event B occurs given event A has already occurred. So when you see this vertical line, I would like to make it a little longer so it doesn't look like the letter I. When you see that vertical line, you read that as given. Okay, so same thing here. Let's make this a little longer. It's not an I, it's a vertical line. All right, how do you decide if two events are dependent or independent? Well, let's try this example. Event A, a baby girl is born. Event B, a baby girl is born into a different family. Do you think these events are dependent or independent of each other? If you said independent, you're correct. This baby being born, they had a 1 in 2 chance of it being a girl. And if that baby was already born, it does not change the probability that another family has a 1 in 2 chance of a baby girl. Let's try this one. The King of Hearts is drawn from a deck of cards, and it's not put back in the deck. Then a 9 of clubs is drawn from the same deck. Do you think those events are dependent on each other or independent of each other? If you said dependent, you are correct. Once event A occurs, so the King of Hearts is drawn, that was a 4 out of 52 chance of occurring. But that king was not replaced, so now there are only 51 cards left in the deck. So the 9 of clubs is drawn from the same deck. There are 4 9s. And had event A not occurred, it would be over 52. But since event A did occur and it affects our denominator, it changes the probability of event B. That's what makes them independent. Okay? All right. Note that if without replacement from a finite group is specified, then the events are automatically dependent, okay? So if you see the wording not replaced, you can just quickly go, okay, dependent events. All right, let's try an example. 3 different people are randomly selected from your class. Find the probability that they are all born on a Monday. Give your answer to the nearest 1,000th. Okay, these events are independent of each other. One person being on a Monday does not affect their classmate being born on a Monday or a different day of the week. So we're going to use the top rule from the last slide, where we take the fraction for probability of event A occurring, multiplication, probability of event B occurring, and we're going to have a third event, so we're going to multiply it by the probability of event C occurring, because we are going to talk to 3 different people. All right, so setting up as a blank template would look like this. Fraction bar, multiplication, fraction bar, multiplication, fraction bar. So you have 1, 2, 3, 4, 5, 6 blanks to fill in. Starting with your first 2 blanks, try to ignore the other ones, just focusing on what's the probability of asking one person what day they were born and them saying Monday. Well, there are 7 days in the week, so that's 1 out of 7. You go to the next person, same thing. You ask them what day of the week they're born on, there's a 1 in 7 chance they're going to say Monday. You go to the third person and ask them what day of the week they were born on, there's a 1 in 7 chance they're going to say Monday. Multiplying those all together, 1/7 times 1/7 times 1/7 is 1 over 343. We were asked to give this answer to the nearest 1,000th, so if you do long division or type that in a calculator, you'll get 0.003. All right, let's try another example. 50 drug test results are given from people who use drugs. If 2 of the subjects are randomly selected without replacement, to the nearest 1,000th, find the probability that the first person tested positive and the second person tested negative. Okay, so we are talking about the probability of event A occurs, and then that changes the probability of event B occurring. And that is because once person A is picked out of this finite group, they are not put back in the group. So kind of think of it like this. Once person A is selected, there's no longer 50 people to draw from. There are only 49. Furthermore, once that person A is selected, it says that the first person, we're finding the probability that the first person tested positive. So the first person is out of this group of 44. So that would then decrease. There would only be 43 left. So now you can see the numbers are totally different. So when you're setting up your fraction for the probability of event B occurring, given A already occurred, you're working with different numbers. So these are dependent events. Let me erase all that and let's set it up. All right, the probability of first person testing positive is 44 out of 50. Then those numbers change. Our new table would look like 43 and still 6 up there with negative and a total of 49. Okay, that is why the probability of event B occurring, given A already occurred, is 6 out of 49. We're going to multiply those two fractions together, and that will give us 264 over 2,450, which is approximately 0.108. All right, I would like you to pause this video now and try these 3 examples. All right, welcome back. Let's see how you did. For number 1, if you put, 1 over 133,225, you got it right. And they didn't ask us to approximate. That's why we're giving that exact answer there. If you did not get it right, walk through the steps here. 2 different people are selected, and find the probability that they're both born on November 24th. So there are 365 days in the year, and November 24th is just one of those. There's only one November 24th. So when you walk up to the first person and say, well, what day were you born on? There's a 1 in 365 chance they're going to say November 24th. Then you walk up to the second person, not affected by the first. These are deep independent events. You ask them, what day of the year were you born on? There's a 1 in 365 chance they're going to say November 24th. So that's why we're multiplying 1 over 365 times 1 over 365. Number 2 seems, at first read, it's like this is the same problem. I do it the same way. But be very careful. Number 2 is a little different. If you put 1 out of 365, you are correct. All right, let me walk you through this one and why it's different. There are 365 days in the year, so that's the same. We see our denominators are still 365. And the change comes in with the numerator. Notice that the probability of event A, it was 1 over 365 when November 24th was considered the success. But now notice that it is 365 out of 365. The reason for that is success has not been determined. There's no specific date that says this birthday is considered the one success, this day. So when you walk up to that first person and ask them, what day were you born on? It doesn't matter what they say. There are 365 days that they could say out of 365 because there's no determined success yet. However, now that they say their birthday, let's say they say October 1st. Now October 1st has been declared the success. That is the date, October 1st. So when you walk up to the second person, they have a 1 out of 365 chance of saying October 1st. So similar problems, but quite different answers there. So focus on those 2 questions, rewind and go through those a couple times if you need to. Number 3, if you got that right, let me resolve that first. If you got number 3 right, you put approximately 0.77 or 1,892 over 2,450. All right, walking through that one, it looks the same as the question on the last slide, but I changed it up a little bit just to test if you fully understood what was going on. Find the probability that the first person tested positive and the second person tested, and here's the change, also positive. So the first person, you have a 44 out of 50 chance that they tested positive. But now the numbers changed. Now we have 43 people up there with a positive card and 49 total. And the second event is that person also tested positive. So we've got 43 out of 49 this time. And that will conclude our discussion on section 4.2. My name is Jami Emigh. Thank you for joining me. See you next time for our discussion on section 4.3.